Welcome to example number 1. Let's suppose you fly a propeller-driven model airplane on a 5-meter long string in a horizontal circle. The airplane has a mass of 0.5 kilograms and flies level, so it's maintaining the same altitude. It's a perfect horizontal circle. And it moves at a constant speed, and as it moves around in one entire revolution, it takes 4 seconds to make that revolution. So we're asked to find how much must you pull on the string, which is the tension, to keep this plane flying in a circle. So the first thing we'll do is we'll pick a body, which is the airplane, I hope you realize, and draw the free body diagram. Let's identify all the forces acting on this object. If you're that airplane, we know you must have weight because you have mass, so there is a force of gravity acting downwards. And we also know that there must be a lift force that is balancing this out. Otherwise, the airplane would not be flying at a continuous same altitude or level. Remember, it's flying in a perfect horizontal circle. Now, the object is moving in a circle, so what force is keeping the object moving in a perfect circle? That would be the string pulling inwards on it, and that is the force of tension. And that's what we're trying to find. What is the tension of the string? How much must you pull inwards? Now, by the way, there are other forces. You probably could draw a backwards force here, by the way, called F sub D, which is the drag force. And there's probably another force acting forwards, which I could call force thrust, which would be the force due to the propellers pushing it forwards. Anyway, we're not really interested in really the thrust or the drag or the lift and the weight. We're really interested in the force that is keeping the plane moving in a circle. Really, the forces along this axis would balance out to be 0 because the plane is not moving up or down in altitude. And the thrust would be equal to the drag because it's not speeding up or slowing down. It's maintaining the same speed. But the object is indeed accelerating, and it's accelerating towards the center of the circle because it's continuously changing its direction. Remember, velocity is a vector. So it's the tension that is providing this net inward force. Okay, so now that we've established the free body diagram, let's choose a axis where we're going to apply Newton's second law. And that would be this axis right along here, right along the radius of this circle. We're going to apply Newton's second law. The sum of the forces equals ma. And we're looking at along this axis right here, so that would be that acceleration is that special type of acceleration called the centripetal acceleration. So the net inward force is equal to ma sub c. We know that the centripetal acceleration is given by v squared divided by the radius of the circle. So let's substitute that in on the right side. We have mv squared over r. So this net inward force, or centripetal force, is due to what force? What's keeping this moving in a circle? It's the tension. So the tension is equal to mv squared over r. And that's really what we're asked to find, is the tension. So what do we know is given in the problem? Let's just write down, make a list of all the given information in the problem. We have 5 meters. That's the distance from here to here. I'm assuming roughly, we're not including the length of your arm. So we're going to assume that the axis here to the middle of the airplane is roughly r of 5 meters. And we have the mass of the airplane, so m is given as 0.5 kilograms. And we're given that it makes one revolution in 4 seconds. So the 4 seconds represents the time to make one revolution, which we call the period, which we represent with a capital T. And so the capital T is equal to 4.00 seconds. Is there anything else that I'm missing here? No. So I know the mass, I know the radius, I don't know the speed. But I could calculate the speed. Remember, the speed is given as the distance that it travels in a circle divided by the time. The distance that it travels in a circle is called the circumference. And the circumference is given by 2 pi r. And the time that it takes to make one revolution is called the period. So you could either calculate this right now, you could plug in your r and your period of 4 seconds and figure out what the speed is. It's going to be probably around 7.85 meters per second. Alternatively, you could substitute it into here. So let's do that because that's what we're just looking for, the tension. So we're going to replace v with 2 pi r all over the period squared divided by the radius. And so now the tension will be equal to 4 pi squared m, and then an r squared, and then the t squared will be in the bottom with the r. Oh, we can cancel out one of these r's, and so we get now 4 pi squared m times r divided by the period squared. So now all we have to do is substitute in. So 4 pi squared times the mass of the airplane, 0.5 kilograms, times the radius of the string, which is 5 meters, and then all divided by the period, which is 4 seconds, quantity squared. So if you put that in your calculator, you'll find that the net force, or the net inward force, which is the tension in this case, is 6.15 newtons. If you write this as a vector, by the way, it has a magnitude of 6.15 newtons, and the direction is inwards, towards the center of the circle. Very common mistake that people will say is they'll think of the force being outwards, because if you were in that airplane, you might say, yeah, isn't it kind of pushing me outwards? Well, that's what you feel. But really, the real force that's acting on this airplane is the tension. The airplane has a tendency to move in a straight line due to inertia, but if it weren't for the string, then the airplane would just continue moving along in a straight line. It doesn't do that. It continues to actually go in a circle because of this tension. So the real physical force acting on the airplane is directly inwards. Okay? There's another force that people sometimes talk about called the centrifugal force. That's that imaginary force that you feel like you're being pushed outwards, but that's not really what's happening to you. That's just due to inertia. Okay, and that's it for this example.